Welcome back, Physics 11, to another episode on a specific type of force. So in today's video, we're going to be learning about tension. So just to get us started, just know that tension occurs within a material that is being pulled or stretched. Now, another important fact about tension is that it is an internal force, so it's acting within the rope. It's also acting at all points along the rope, and it's also happening simultaneously in both directions. So one way of kind of visualizing that or making it a bit easier to understand, imagine that you have a number of people who are all lined up and they're all holding hands. So we've got all these people standing together, they're all holding hands, and there's a big stream of them, right? So with these people that are holding hands, if we look at the tension in their arms, is there anyone, so let's say this person's being pulled this way and this person's being pulled this way. Even if you were in the middle of the rope, is there anyone there who wouldn't be feeling that tension? No. Every single person in that chain is going to feel tension, and every single person in that chain is going to simultaneously feel themselves being pulled in both directions. So it doesn't matter if you're talking about this person or this person or this person or this person, they're feeling tension acting in both directions, and they're feeling it at all points along the rope there. So that's kind of one way of just thinking about why it's acting at all points and why it's acting in both directions. Let's look at an example problem here. Let's say you have two carts that are attached by a rope and they're being pulled along a flat surface, and we're going to ignore friction. We're going to say it's negligible, meaning the size is so small it doesn't really play a part. So if M1 is being pulled to the right by a force of 40 newtons, what is going to be the acceleration of the carts? And so a couple bits of information that I did not put in the question. This mass here, we're assuming this is 6.0 kilograms, and this is going to be 4.0 kilograms. That's the masses of the two. Now, what we should always do with our diagrams here is we should always include we should always include a free body diagram. So for this free body diagram here, what are the forces acting on it? So I'll give you a second to think about it. You can pause the video if you want, but I want you to think about what forces are involved. So number one, we are going to have a normal force for both of these objects here, and that's going to be counteracted by our gravitational force. And because they have different masses, the way I've indicated it here, I've said that this one and this one are equivalent to each other. We know that because they're not accelerating up or down. And I've said that this one and this one are equal to each other, again, because they're not accelerating up or down. But I've indicated this one with one line, this one with two lines to tell you that, this gravitational force on the 4 kilogram is not going to be the same as the gravitational force on the 6 kilogram. We also have the force of tension acting in this way, and we have the force of tension acting in this way. But again, the important thing about tension is that we recognize that it acts in both directions, and it's all going to be the same at all points. So the tension pulling this cart to the left is going to be the same as the tension pulling this cart over here to the right. And then we have one more force here, which we said is a 40 Newton force pulling this first cart to the right. So when we want to solve it, we can solve this the same way that we always do. We know that our net force is equal to mass times acceleration, and this is equal to the sum of our forces. Now, in this case, I'm going to do them all in full. So I'm just going to show you what forces are involved. So if we look at our diagram, there's a total of 7 forces. We've got Fg1 plus Fg2 plus Fn1 plus Fn2 plus force of tension 1. I'm going to call this Ft1, and then I'm going to call this Ft2 plus our applied force, this 40 Newton force. Now let's take a look at which ones cancel out. Well, Fg1 and Fn1, those are both going to cancel out. Fg2 and Fn2, those are both going to cancel out. Ft1 and Ft2, those are both going to cancel out. Again, all of those pairs that I just mentioned are equal and opposite. So this makes our job a little bit easier. Once we've done this analysis of it, we recognize that our formula is just going to boil down to the following. M times A equals our applied force. And when we're looking at this, when we're talking about the net force, it's important to recognize what is the object that we're referring to. So I'm going to draw a box around the quote object that we're referring to. And this is where kind of thinking about how we analyze the problem comes in handy. So the object that I'm referring to is this entire object that remains within this colorful box. All of the object or the entire object consists of these two carts plus the rope plus whatever rope is pulling it from the front. But this entire thing we're going to treat as one object. So if we're treating this as one object, what is the mass of this one singular object, this thing that remains inside this colorful box? Well, the mass is going to be a total of 4 plus 6, which is going to be 10. So 10 times the acceleration is going to equal our net force, which we said was 40 newtons. And so therefore, I'm sure we can all do the math there ourselves, but the acceleration is going to be 40 divided by 10, or 4 meters per second squared. That's how we would go about solving that. So the thing to notice, the tension is going to cancel out. Tension cancels out of the total net force equation. So that's when we're looking at an entire object that's all within this colorful boundary that I've drawn here for you. Okay, what about if we want to find the tension in the string? Well, if we want to find the tension in the string, we have to change the scope of our problem. If I try and solve the tension in the string with everything that lies within this colorful box up here, well, there's no way for us to calculate that. There is a tension to the right, but there's an equal and opposite tension to the left. And so in our equation, we're always going to have plus tension minus tension. We have no mathematical way of solving it when we're looking at this whole picture. But we do have a way of solving it if we change our scope. So what I'm going to do this time is now, instead of looking at the entire picture, I'm going to limit my picture to just one object. So in this case here, I could choose this as the object that I'm looking at, so everything that lies within that circle, or I could choose this as the object that I'm looking at, everything that lies within this circle. Now, when we're doing that, we have a choice to make in terms of what's going to make our life simpler. So pause the video if you need to, but think about which of these two boxes or which of these two objects would we rather use to solve the net force equaling the mass times the acceleration. Now, hopefully you don't have to think for too long. Hopefully you can look at this and say, well, the box that's to the left here, this only has one force acting on it. So if we're looking at our net force being the sum of all of our forces, well, we're only going to have one if we look at this box on the left. If we look at the box on the right, we're going to have two different forces. We've got tension and we've got this applied force, and so our sum of our forces would equal two different forces. So the easier one to work with is obviously the one that just has the one force on it. So let's look at this force on the left. We can go back to our same fundamental principles. We have our net forces, our mass times acceleration, and this is going to equal the sum of all of our forces, which in this case is just Ft1. So now let's go back and see what those variables are. Well, what is the M of everything inside this box? Because remember, this is now the only thing that we're looking at is what's inside this box. So this is going to leave us with, I'm just going to change the color now, 6 is our mass. Our acceleration we've already found here is going to be 4 meters per second squared equals Ft1, and there's our answer. So the tension force on this one over here is going to be 24. Now, we know right away, because we know the tension is equal and opposite, so we know that the tension force Ft2 should be 24, but let's take a little detour and let's try and solve that again just to confirm that. So I'm going to do the same thing we did before. We have our mass times our acceleration equals the sum of our forces, which in this case is the applied force plus the force of tension 2. Now, if I'm looking in this front box up here, so that's what this formula here is going to be for, then we have 6 times, sorry, the mass of this object is 4 kilograms. So 4 kilograms times 4 meters per second squared is going to equal our FT2. So I'm going to say FA plus, sorry, FA was the 40, my apologies, plus FT2. So now we have 16 equals 40 plus FT2, and therefore we have negative 24 equals FT2. I've just subtracted 40 from both sides. So negative 24 equals FT2, and that exactly lines up with what we would expect. If FT1, we're calling that a positive 24 because it's to the right, then FT2 should be negative 24, and so we've proven our idea as being correct. So, a couple of important things to note. Since it cancels out of the total F-kinetic equation, we will only consider forces acting on one mass. So that's what I did there, is looked at it acting on one mass, either the mass on the left or the mass on the right. And seeing how tension acts on both masses equally, we can use either mass. So both of them would, as we've just seen, get us the correct answer. Okay, what about this question here where we're dealing with pulleys? So one bit of advice that I have is when you're drawing the diagram, you should unfold the rope as shown. In fact, I'll just highlight that one part there. We're unfolding the rope as shown. So what I mean by that is if I take this diagram that's on the right-hand side here, what's happening here? Okay, take this diagram that's on the right-hand side, and I'm going to, unfold this up this way, unfold this up this way. So now it looks like it's going to be one flat line. And we also have to move the forces that go with that. So in this case here, there's Ft and there's Ft, and these two will be equal. So tension is going to be equal. For this system here, we're going to consider this mass to be, actually this is just a diagram, so we don't need to worry about the mass. I'm going to call this M2, so I'm going to call this Fg2, and this will be Fg1. And I'm just assuming in this case here that the mass 2 is heavier, so we can see it's going to be a larger gravitational force. So if we are unfolding this, then the direction of our arrows should look like this. This will be our Fg2. The direction of the arrow kind of goes with the system here. When we unfold the rope, Fg2 is now going to be to the right, and we've got our two tension forces here, and then we have Fg1. So this is just how we can unfold this diagram to make it a bit easier to kind of see what's happening here. So we can see here that the tension forces are going to cancel out, and overall we have a large Fg to the right, a small Fg to the left, so we'd be able to show that it's accelerating to the right. So what I'd like you to do is try an example here. These values here, 6 and 4, these are the masses of them in kilograms. So try this system out for yourself and see if you can determine what the acceleration is going to be. And then using the same method that we tried above, where we isolate it to just one mass, let's see if we can solve for the tension. So pause the video now and see what you come up with for your answer. Okay, well, hopefully you have tried solving this on your own, and if so, we're going to go over the problem ourselves. So, in this case here, I'm going to draw all these forces out. We know that this is going to be Fg, I'm going to call this Fg4 for the 4 kilogram mass, Fg6 for the 6 kilogram mass, and we have two tension forces that are going to be equal and opposite. In terms of my system here, I'm going to look at the entire object. So let's look at all the forces that we have here. Well, our net force is going to be our mass times acceleration. Now again, we're looking at the mass that lies within our scope. So in this case, the colorful box. So this is going to be m times a, and this is going to equal the sum of all the forces. Now, in this case here, do we need to write down F plus Ft minus Ft? No, those are both going to cancel themselves out. So I'm just going to write down that this is going to equal Fg6 plus Fg4. So if we continue with that logic, we've got 10, our total mass, times acceleration. Now what is Fg6 going to be? So we know Fg is mass times our gravitational constant. So this is going to be 6 times 9.8. And 6 times 9.8 is 58.8. So I'm just going to label that here. This is going to be 58.8. And 4 times 9.8 is going to be 39.2. Okay, so feel free to get into the habit of annotating your diagram. It does kind of help sometimes with our solving our problem here. Now, when you're looking at this, you should also keep track of which direction these two forces are going. So in this case here, Fg6, I'm going to call this negative 58.8. It's pointing to the left, plus 39.2. So 39.2 minus 58.8 is a total of negative 19.6. So carrying on here, 10 times A equals negative 19.6. Divide both sides by 10, and A equals negative 1.96. So that's going to be our acceleration, and it's going to be moving to the left, which is why we called it negative. Or in this case here, on our redrawn diagram, it's to the left, but in this case here, it means it's going to be going counterclockwise around the pulley. Now let's try and solve for the tension in the string. And so for the tension in the string, we're going to look at just one object here. So I'm going to change my scope. Again, you could choose either one, but I'm going to look at this one here. So for this box that's on the left-hand side, let's take a look at all the forces involved. So M times A equals the sum of our forces, which in this case here is Fg6 plus Ft. The mass of the 6 kilogram object is 6. We know the acceleration was negative 1.96, and this is going to equal negative 58.8 plus the force of tension. Again, the Fg was negative because it's going to the left. The acceleration is negative because it's going to the left, and so we should be able to solve for that. So what do we get when we multiply 6 times 1.96 is going to give us negative 11.6, sorry, negative 11.76. So negative 11.76 equals negative 58.8 plus Ft. I'm going to add 58.8 to both sides, and I have Ft equals 47.04 newtons. And that's going to be our final answer for part B. So there we go. So just to summarize the key ideas here, when you are solving for acceleration of the whole system, we have to consider the total mass. But when we're finding t, we're only going to use one mass. Okay, last couple questions. Again, try and pause the video and try these out on your own, and then we'll answer them together as a class. The masses are, or we'll answer them together on the video. The masses are just as listed there. So 8 kilograms and 6 kilograms for those two masses. Try them yourself, and we'll come back and solve them when you're done. Okay, so I'm going to go through these quickly in the interest of keeping the video below 25 minutes long, but let's take a look here. So in terms of our forces, we only really have the one force acting on it that's going to make a difference. These tension forces are going to cancel out. The normal and gravitational force is going to cancel out. So this is the only force that's acting on this whole system. And again, I'm considering the system to be this entire object here. So when I redraw this, this is what I have in terms of relevant forces. So if our F is equal to our mass times acceleration, which is going to be the sum of our forces, in this case, the only force is a force of gravity on the 6 kilogram mass. So this is the net force of the whole system. So this means that we're going to have to use the net mass. So 14 times A equals Fg6, which is going to be 6 times 9.8. So this is our Fg6 is 6 times 9.8, and that's going to be 58.8. If I divide by the total mass of the system, I'm going to have acceleration equals 4.2 meters per second squared. Now, if I want to know the tension in the rope, I've just got to narrow my scope down here a bit. And so the scope, I'm going to use this 8 kilogram block. Again, I'm choosing to use that one because it only has one force acting on it. Whereas if I chose to use the 6 kilogram block, we know there'd be two forces. There'd be the tension force going up and the gravitational force going down. So if I want to find the tension, again, our net force, I'm just going to start skipping some steps here instead of being so repetitive. So m times a equals the sum of our forces. In this case, there is only the tension force if we're looking at this 8 kilogram block. Normal and gravitational force cancel out. So 8 times 4.2 equals our force of tension, which in this case is 34 newtons. Not too bad. Now, what about if the same system had a friction force of 25 newtons acting on this 8 kilogram mass? So again, there are gravitational normal forces that cancel out. There's tension forces which cancel out, but now there's two forces remaining that are going to affect acceleration. So if we redraw this here, we're going to have this force here is 25 to the left. I'll just call it 25. So 25 to the left. Then we have our other block, and over here we have this force which we've already determined was 58.8. So if we want to solve the acceleration of the mass, we have the total mass times the acceleration of the total system. Again, we're looking at the entire object here, is going to be equal to the sum of our forces. Now, the sum of our forces is going to be 58.8, this gravitational force to the right, plus negative 25, which is our friction force to the left. So 58.8 minus the 25 is going to be 33.8. So the total mass is 14 times A equals 33.8. In this case, it will obviously be less acceleration than the previous example, and in fact, our acceleration equals 2.4 meters per second squared. So you can see it's much less than the 4.2 meters per second squared that we got when there was no friction. And last but not least is our tension force. Now, in this case, both of the objects have two forces acting on them. So I'm going to go with this one that's on the right-hand side here, and this is my formula to solve this. So the total mass of the object in question, which is that 6 kilogram mass, times its acceleration, is going to equal the sum of our forces. So in this case here, I'm going to say 58.8. We know it's accelerating to the right. So if I redraw this, I like redrawing it this way. Again, we're looking inside this box here where we have tension and we have gravity. So that's going to be our tension force. This I'm going to call 58.8 as a positive number because my acceleration was 2.4 as a positive number. It's going to the right in this case here. So carrying on from there, m times a equals 58.8 plus the tension force. So 6 times 2.4 equals 58.8 plus force of tension. And this gives us minus 58.8. We have negative 44.3. I've just kept all the significant figures from my previous equation there. So negative 44.3 newtons, and that would be our final answer for the tension force. So, as always, complete any practice questions you have, and if you do have any questions, come see me during Fit Block or see you on the Monday meeting. Thank you.